Hi everyone, my name is Min Cho and I'm the team leader for this 21st Kwix conference. We are the Semiconductor and Nano Device Lab from Kwang University, which the advisor is Sangmo Koo. Today, I'd like to represent our research on minimizing short-channel effects of 4H-SiC CMOS inverters for aerospace application at 500 degrees Celsius. So, let's get started. Here's the outline of my talk today. First, I'll give a short introduction, explaining why 4H-SiC CMOS inverters matter for aerospace devices. Next is the experimental part. I'll go over the main ideas we used to optimize MOSFETs. Then we move on to research and discussion. I'll show IV curves and look at the parameters with channel lengths. At least, talk about how we optimize the channel length and verification with potential distributions. Let me start by giving some backgrounds. NASA has already shown that SiC JFET inverters can work at 500 degrees even in mission like Venus landers. But JFET circuits are limited because they cannot scale well. That is why we focus on CMOS. 4H-SiC CMOS inverters combine thermal resilience with higher integration and faster signal processing. Our goal is to prove stable CMOS inverter operation at 500 degrees by minimizing short-channel effects. This can lay the foundation for future high-temperature aerospace electronics. Also, comparing silicon MOSFETs and silicon carbide MOSFETs is crucial. Silicon has a small band gap and cannot handle high temperature. In contrast, 4H-SiC has a wide band gap, high thermal conductivity, and a much higher critical field. This allows silicon carbide devices to work at a higher voltage, power, and temperature. When applied to CMOS inverters, we gained higher integration, faster speed, and reliable operation in harsh environments. So, silicon carbide is not just a replacement for silicon. It enables performance that silicon cannot reach. Before the results, let me explain key concepts. First, threshold voltage. In short channels, it makes rolls off, so the device can turn on too early and the control becomes difficult. Second, mobility. As the field increases, scattering grows and mobility drops. It's so crucial problems. Third, DIBO. The full name is drain-induced barrier lowering. Like the full name, the drain lowers the barrier and weakens gain control. And finally, channel length modulation. The channel length modulation makes the current keeps rising instead of saturating. These are the main short channel effects we need to overcome. Here we show the basic structure of our lateral SiC MOS and PMOS devices. We can see the two-dimensional cross-section on the top with the source, drain, well, and epi layers clearly defined. The detailed process parameters are summarized in these tables below. Among them, two are especially important for our study. The device width, which is set to 150 micrometers, and the channel lengths, which are verified from 1 to 100 micrometers. These parameters are the key factors that directly affect short channel effects and the overall device performance. First, we extracted transfer characteristics with the drain voltage fixed at 0.1 volts. At room temperature and long channel lengths, we see a relatively high threshold voltage. But as the temperature rises to 500 degrees, the slope of the transfer curve becomes more gradual. This means the transconductance decreases, threshold voltage shifts down, and the leakage current increases. Also, when the channel length is reduced, the threshold voltage drops further, showing stronger short channel effects. If we compare MOS and PMOS, the absolute drain current of a PMOS is clearly smaller than that of the MOS. So, for CMOS design, we need the stable threshold voltage and low leakage. We need to enlarge the PMOS width for current balance, and we also need to manage drain current saturation under high temperature. Next is the output characteristic. At room temperature and with a long channel, the MOS shows a clear saturation current. But with the temperature rises to 500 degrees, the drain current keeps increasing even after saturation. This comes from short channel effects where both channel length modulation and DIBO reduce the output resistance. When the channel lengths become shorter, these effects are more simple. The result is higher drain currents, which is good for faster switching, but at the same time the linearity is degraded. So we need the minimum channel length to secure stable operation. For PMOS, the trend is similar, but the absolute drain current is much smaller than NMOS. We have to consider this in the CMOS circuits. In this analysis, instead of covering the full range from 1 to 100 micrometers, we focused more closely on the range of 1 to 10 micrometers. Now, let's see how mobility changes with gate voltage. NMOS reaches its peak at a lower gate voltage because its threshold voltage is smaller, but PMOS needs a higher gate voltage. When the temperature goes up, mobility also increases since column scattering is reduced. But short channels shows strong lateral fields and velocity saturation. As the result, mobility drops quickly. This shows that the short channel limits controllability, so mobility optimization is important. Next is the threshold voltage trend. For NMOS, threshold voltage drops from 2.63 to 2.13 volts at 500 degrees at the channel stretch from 10 to 1 micrometer. PMOS also shows the decrease, but it stays above 5 volts. This happens because of the charge sharing and dipole, which weaken gate control. NMOS at 1 micrometer may even turn on unintentionally due to noise. The mean of the channel length has to be optimized utilizing the capability of short channel devices while maintaining stability. Now, let's check specific on resistance. As the channel becomes shorter, specific on resistance goes down sharply. For NMOS, it falls from almost 2 to 0.04 at 500 degrees. PMOS shows higher values because the hole mobility is lower. At high temperature, more free carriers appear and the column scattering becomes weaker. This makes lower resistance even more. So, short channel improve switching performance, even though they also bring stability issues. Here we see mobility as a function of channel length. At 500 degrees, NMOS drop from 45 to 11, even when scaled from 10 to 1 micrometer. PMOS also drops from 8.7 to about 4.3. So temperature improves mobility overall, but short channels suffer from dipole and velocity saturation. NMOS always shows higher values than PMOS, but both degrade as the channel gets shorter. This means we must optimize the channel length to balance speed and reliability. So the question is what length gives both stability and performance? We check the ratio of drain current at 20 volts and 10 volts. When the ratio is higher than 1.1, short channel effects dominate. Using this method, the optimized length is 1.7 micrometers at 500 degrees for NMOS. PMOS shows almost the same trend. So we conclude that 1.7 micrometers is the minimum safe channel length for both devices. Here we verified the result with potential distribution. In short channels, the drain field penetrates under the gate. The source barrier becomes lower and the dipole appears. In long channels, the drain effect is confined to, so the barrier is preserved. But resistance is high and integration is poor. At 1.7 micrometers, the penetration decays smoothly and the source barrier is stable. So this structure confirms that the optimized length is valid. To sum up, we found 1.7 micrometers as the optimized channel length at 500 degrees. This value suppresses short channel effects and secures stable current saturation. It also enables reliable switching. With this, silicon carbide CMOS can be used in harsh environments like aircraft engines, Mars rovers, and high temperature sensors. By optimizing MOSFET parameters, we can build CMOS circuits for the next generation of aerospace electronics. Thank you for listening.